going to be about Hitachi. So it's like a very difficult moment for me right now. First of all, I'm not supposed to be here. I'm their second choice. The true story. So a few months ago, they wrote Scott Myers and said, would you want to give a keynote at C++ Europe? And Scott said, well, no, but I know a guy who can do a very good Romanian accent. So I was their second choice. They said, Scott couldn't come, but maybe you can. So it was kind of interesting. I was like, okay, so I get to see my parents. This is going to be awesome. I'm going to talk to my students, so I'll be very happy to visit. So that was months ago. And as it always happens, when you make a commitment that's going to be a few months in the future, it's not too bad at the time, right? It's like marriage. It's like, yeah, we can marry, no problem. I'm going to deal with it when it comes. So the time comes, the time window compresses to the point where at some point I had to be like, what am I going to talk about? And at that point I had a great inspiration, which was Wikipedia. So actually I have a page on Wikipedia that I have nothing to do with. I didn't publish it or anything. It's other people. And the page on Wiki, you can browse it right now. You're going to see there's like some sort of a disclaimer at the beginning. And it says something like, this guy is not really the caliber we need here for people on Wikipedia. So he's not really good. I think there's one guy who, I saw discussions and stuff, I browse it every a few months or so. Every few months there's a guy who says, is this guy deserving of Wikipedia, of being on Wikipedia? Who's this guy after all? So there's this ongoing controversy about me being on Wikipedia, which is very funny. And anyhow, so recently, a few months ago, when I browsed my Wikipedia page again, I figured out somebody went there and there's a section with contributions or something like that. So they deleted everything I did and they put one piece of work. So I thought I'm going to talk about that. This must be important to some people, so let me talk about this thing. So the history of this is in 2012 at a conference called C++ and Beyond, I talked about an idea I had, which was unexpected type. And as it happens in Karamazov, right, in Dostoevsky's novels, some crazy guy took the idea and ran with it. And actually two crazy guys, and they kind of it gained momentum and stuff. And right now it's being proposed for inclusion in C++ 20 standard. So I thought it's kind of a cool thing to talk about. So this is about expected, but before that, we should fix the slides because there's going to be no titles if we continue like that. Yeah. So can you actually? I guess if we. Okay, give it to me because I'm the technical guy in this room, right? All right. So I guess I'm gonna try it again. There we go. All right. Where's the applause when you need it, right? Thank you. All right. So exceptions. Who likes exceptions? Okay, that's my audience. That's okay. So you use C++. I'm not at a Python event here. Go, right? This is not a Go event. All right. By the way, who's using C++ professionally on a daily basis? An appropriate question. Not everybody, but most of you. Right. So exceptions. It's kind of funny. Like when I learned about exceptions, all of my functions I try and catch in them because it was kind of the cool thing to do. Right. And discover templates. Everything has a template in it. And then discover whatever, and everything has a whatever in it. So most of us took exceptions. Well, it's a feature, so you got to use it. So I want to rediscover exceptions to see what they're about. Kind of do do a reverse engineering of exceptions. Let's see what's happening. By the way, I should add two more things before we get into the technical thing. First of all, this is supposed to be a keynote. They said, oh, this is the first C++ Europe event. We want a good keynote to come with it. And I don't do keynotes. I do tech talks. I don't, this is supposed to be like inspirational, kind of high level and super. No, it's going to be code on the slides, okay? Just as a warning. Thank you. Yes, that's great. So are you happy with that? Is that okay? It's going to be code and stuff, right? Okay. Like union. There's going to be union. I'm not kidding. Like there's going to be union somewhere. Okay, good. Second thing, I mean, this is the first edition. We're already part of history. We imagine the responsibility we have right now, right? So even if you don't like this, please pretend you like it, okay? So what would be a proper baseline? So what do you compare exceptions against? What would be other good ways of handling errors that we would compare and contrast exceptions against? What are the design goals of exceptions? Intended use cases? How do the exceptions once used support those use cases? What are the consequences, the new setup, and things like that? And it turns out like the community took literally decades to figure that out. It's kind of interesting. Like I remember there was a time when people said exceptions are the be all and all of C++ or error handling, and then came an article, and I remember it was the late 90s. Come an article by Tom Cargill, which said the title was "Exceptions: A False Sense of Security." He showed that a number of simple transactional idioms could not be expressed with exceptions. So that kind of was quite a bummer. So how do we write code playing into their strengths? So we want a error handling mechanism that you learn once and use many times. We would like to minimize what's called soft errors and maximize hard errors. What in the world would that be? I'm actually taking, it's not a rhetorical question. So I'm taking from the audience, like, what's a soft error versus a hard error? Yes, please. The software, the computer does not necessarily know how to handle it. So that would be a different universe. Software I call a dangling pointer. You don't discover it immediately, right? It may not even manifest itself at all. So you don't know it exists, right? It's a software. Hardware is like the computer can actually discover it right now, and it stops execution, right? So what are the bad errors? Which are the ones you don't like? Of course, the soft errors, because those are much more difficult to deal with. So we want to minimize soft errors. We want to maximize the hard errors. We want to know whenever an error is happening. We want to avoid the metastable states. You know, these applications that once you have an error on the application, you better quit right now because otherwise, right? Because it's kind of, it goes on oil, right? That's a Romanian expression, right? It goes on oil, like a drunk person, right? Okay. Well, this is an event in English, but it's in Romania, right? So I'm going to use the Romanian proverb now and then for good measure. So we want to keep the error handling separate from most code because we want some sort of a good modularity, if you wish, of error code as opposed to normal path code. I'm going to go just a bit forward if you allow me. Just a little. This. Did you see that? It's a joke. Any Go programmer enthusiasts in the room? A joke about the Go language in which these lines of code are so frequent. It's actually transporting their the error is in the main path of execution, so you have to handle it everywhere. So these lines of code are so frequent that somebody made the joke and put them on a keyboard. That brought down the whole house, right? No matter how bad this joke is, I'm gonna just use it. All right, so we want to allow centralized handling, but sometimes we do want local handling, so we want the option, really. We want to have the option of being local or centralized. We want to transport an arbitrary amount of error information. An integer is not always enough, right? We want to demand as little cost on the normal path as possible. This is kind of a long discussion. Maybe we'll get into it. And we want to make correct code easy to write foremost, right? First and foremost. Great. So let's start with a simple function like a2y in the standard C library, which returns an integer and from a pointer to character, from a string. Now, the funny thing about the design of a2y is if anything bad happens, it's going to return 0, which is about the most frequent number in the universe, right? Like I bet you money that in most C and C++ and other languages programs, the most frequent number right now is 0. Like 70%, right? And most strings are what? Empty, right? Most strings are empty. Most floating point numbers are nan, because nan propagates. The hell with it, right? I hate that. The J when it happens. So anyhow, so HY is about the worst designed function you can invent because it returns a very common number for in the error case. And the funny part is if you want to use H2I and it returns 0 and you want to discover whether it was a legitimate 0 or actually a bad, an error happening, you would need to write a little parser because this is a 0. This is a 0. It's a space followed by a 0. Could be a space, a tab, a backslash, and backslash r, right? Space plus 0, 0, 0 is also a good input. So you have to write a little A2I to figure out whether A2I was correct or not. So that takes us to kind of an unpleasant conclusion that, well, A2I returns any possible integer, so it can't return just int. It must return int plus plus, right? It must an int and a little extra outside the int, right? So the sheer bits in the int are not enough because it's a subjective function, right? This like, this highly mathematical scientific term you may not be aware with because you forgot high school, right? Surjection, a function that covers its entire code domain, right? Okay, so I want to distinguish the valid from invalid input properly. So this would be an example of a poorly designed function that way. And it's actually unrecognizable. If you Google for it, you're going to see like Stack Overflow. Oh, how do I figure out if A2I was correct or not? And you can't. And that kind of stuff, Stack Overflow, gotta love it, right? So let's talk about Erno. Who likes Erno? Even fewer people than exceptions. Okay, so that's progress. So it looks like, there are like 2 hands up for exceptions and 0 hands up for Erno. So, this is like infinite ratio, right? This is awesome. So Erno is, generally we can, you just set Erno and you're done, so you can do that in any function. It does not minimize soft errors for the simple reason that nobody looks at Erno. Like nobody, let's face it. Who calls printf and looks at Erno? Come on. Yeah, one guy, yeah, thank you very much. So, that kind of stuff. It does allow centralized handling, so you can actually like pass Erno to a centralized handling function. It does allow local handling, but it does not allow you to pass arbitrary amount of error information. You can't do that. It's just an int. It has a little custom normal path, so that's a good thing, but it does not make correct code easier to write at all. Are we in agreement that kind of Erno is not that cool? Right, so we're looking for something better, right? Oh, and do you know the story with Erno and threads? It's a funny story, right? So Erno, like in the old bad days, right? Medieval ages, right? No toilets, right? Real bad. It was like an int per process. And then people, like the threads were invented, the Renaissance, right? So threads were invented and people start like, oh, so I'm setting error in this thread, I'm reading from this other thread, but actually 2 threads each had their own error. And what are we gonna do? So they said, let's make an exception, let's make error a macro, which forwards to a function, which function returns thread local storage, that's 1 int per thread. You didn't know that, did you? Okay, so it's kind of all that funny information that kind of, it's like you didn't know it existed. So thank you very much for this like completely useless piece of information because I don't like Erno anyway. So, okay, let's move on, I guess. All right, so you can return a special value. Like, what would be your favorite to return in the case of A2Y? Like, let's say we want to reserve an int, sacrifice one lamb, as Alexander said, right? One lamb. We'll sacrifice 1 int value for the worst case scenario in which there's an error. Which would be the int to take the axe? -1? 42. Awesome. The largest integer. The smallest integer. In the middle, right? We'll get back to 0 then, right? So actually, I would choose the littlest, the smallest integer for several reasons. That's a weird number. Because, for example, if you take minus that guy, so I'm talking like minus int min, right? What is that? No, it's not, doesn't have any zero. Minus int min, it's int min. So minus for int min is the only time minus returns an actual negative number for a negative number. And actually, that it has caused like endless amounts of harm to certain programs. And there's another. It does have a. If you essentially, it's the one negative number that does not have a positive reciprocal, right? So it's kind of an odd thing anyway. So let's make that a special value, etc. So that would have been a slightly better design of A2I. So it could return a special value. But that doesn't work with what we called surjective functions, remember. It does not minimize soft errors because people keep on using it, the special value. It does not allow for centralized handling, but you can only do local handling with it. You cannot pass arbitrary amount of error info. By the way, do people in the back hear me? Thank you. I'm asking because like I was at a conference and there's this guy holding his the microphone here, as if the sound came from his belly button, and then he'll keep on turning like his head like that, and he's like, rup, rup. So it was kind of very difficult to understand, right? So 30% I understood from. Okay, so thank you. So we have this situation is not optimal. I'm sure you can appreciate. There will be a NAM for double. There will be a null form pointers, but everything is kind of messed up, right? So now you can actually dedicate a special input to the function. And let me introduce you to the beautiful function strtol, right? Which you know about it, right? It's also in this. It's actually the recommended way of parsing strings into integers. So it takes a double pointer to the kind of the last character that ended the conversion. So you pass into that pointer, and you gotta write like 3 lines every time you call it. You gotta write 3, 4, 5 lines to figure out what happened there, right? So it's kind of unpleasant, right? So not very nice. You can do centralized handling, but pretty much anything else is shot. So not the best solution. So now let's talk about exceptions. So what do you really want an ASCII to integer conversion function to return? You would want something like an integer. I'm going to invent syntax here just a bit. I want an integer or the information that there's an invalid input. So this is like an OR sign, right? A pipe. Either this guy or something bad happened, right? There's some sort of an OR thing. And I want to get it from A to Y and then do some sort of a notice that this kind of blue, like it's a pseudo keyword if you wish. I want to do the switch on the type of the thing. Actually, this does happen in other languages. And I want to say, oh, was it an int, then it's good, and was it not an int, then it's bad. So that would be some sort of a thing with like, and that would make logical sense, and it's kind of motivated, principled, mathematically sound, that kind of stuff, right? So I can only extract the integer if I actually write it down like this, right? So actually, there is some basis for that, which is algebraic types. These are also called discriminated unions and others. So very nice. But there's something even more so because, look at this. This is an integer or invalid input. And, intuitively, this pipe sign, this OR is symmetric. So it could go like it's either this combination or the other combination. So it does not give priority to the fact that I'm actually expecting an int, whereas the invalid input is an exceptional case, is not the expected case, right? So that doesn't really represent the situation clearly because most of the time I'm going to be here, but I'm not going to be here so very often. So therefore, I'm going to say something like, well, I actually expect an integer, or I unexpect, if that's a verb, which it isn't, an invalid input, right? So this kind of gives priority to the integer over the invalid input. It changes the landscape a bit. Agreed? Right? Okay, so let's roll with this a bit. So local code should afford to ignore if they don't care, they should just kind of plow through it and go for the happy case. And in the unhappy case, there should be some other contingency action be done, but I don't want the main path be occupied with error handling. So we should have an overt return type and one or more covert return types. So the obvious question is what happens in the unhappy case? Where should this unexpected go, right? So these covert values should return, but they shouldn't return on the normal path. They should go to some other path. And now we get to really defining exceptions as they are defined in Java, C++, and many other languages, which are we need to have covert execution paths, which are all of the catch statements in a program, right? So I have kind of a distinct way of, the exceptions go a distinct trace, right? Than normal values. And the callers are going to plan return points collecting such types. That's our catch, try catch, right? And we get to this notion of type-based first match exception handling. I should add one slightly philosophical comment. You'll see it's not it's kind of a terrible comment, but let me add this. First match. Does C++ as a programming language do in general first match or best match? Non-rhetorical question. Best match. Who's with best? Depends on as a language. I'm not talking about code you write, but as a language. Does it go for the best match or the first match? Best match virtual functions, right? The most specific caller. Overloading, the most specific overload. Templates, the most specific match, right? So it always goes for the best match. There is one case, however, in which it does first match. Initializer lists. What are those? Oh yeah, exactly. So for initialize, this is gonna pick. It's gonna prefer that guy. So that's gonna be a sort of a. But that's also best match for different definition of best. But there's a case in which C++ does exactly first match syntactic, which is, come on, you guys, catch statements. Catch. So in a catch, it's gonna be tried in syntactic order, essentially the way we wrote them. And you know that bug in which you catch the base first and the derived after, and you never get to the derived case, and your boss is firing you, and all that. It didn't happen to you, it happened to me. Okay, right? So that kind of stuff, right? So this is the only instance I know of in which C++ prefers first match. By the way, there are languages that always do first match, except when they do best match, but always do first match. What languages would those be? Functional languages. So there's a huge debate, what is better, first match or best match? And first match functional people go, if I write my pseudo overloads, as it were, like they write different versions of function depending on conditions, they are tried just like that sequentially. Like factorial of 0 is 0 and factorial of 1, that kind of stuff. They're gonna try it in that order. So it's I'm not gonna comment on which is better, but of course best match is better because it's best. I mean, it's by simple wording, you can't beat it, right? But anyhow, so first match has its place, and in this case, it's indeed first match. So with exceptions, we kind of are left with a big red thing here, which is local handling. You can't do local handling with exceptions properly. And this is kind of an open question whether correct code is easy to write. And in 1998, everybody was happy. In 2008, like the economic crisis, nobody was happy. And right now, we're kind of, maybe we can write good code with exceptions, and you do error handling better with exceptions, and it's kind of undecided. So the problems with exceptions are you can still get into these weird metastable states in which you don't know what happened and what didn't. And it's nice that we have destructors and we have things like scope guard, which, by the way, I think is going to be standardized. I didn't follow on that, but I think there's going to be a form of scope guard in C++. Yes? Could you tell us a few words?
decision.
Thank you.
No decision has been taken yet, so it's
right.
right now under discussion.
So it's on the path to C++20. Under what name? Not scope guard. I know.
Not remember. I
yeah.
don't
So
remember.
is this scope guard or not? This is kind of interesting.
Sorry.
Is that name or a different name?
Slightly different, but
Slightly
I cannot remember right now.
It's kind of funny. Okay, thank you. Thanks very much. So anyhow, so we have these things. Actually, you can Google for that, and it's the 5th hit, because the first 4 are for like rifles with scopes, and they have a scope guard, so there's no dust on the scope. So skip the first 4, and the 5th hit on Google is going to be like this C++ thing. All right, so right, and the whole best match thing is biased a bit. So, with exceptions, I think you agree that it's difficult to analyze code. And Herb Sutter had this very nice series of books, Exception on C++. And actually, I think that he made a lot of money in royalties from those books only by this topic, like analyze how many paths exist in this function. So he shows like a 3-liner, create strings, return strings, add strings, does things with strings. And everything can throw an exception, and the cat, I don't know. So anything could happen at any point in that function. So how many distinct paths are to this function? And of course, nobody gets the answer right except Herb Sutter, right? So it's kind of this kind of funny exercise that really bends your mind. So that's what's kind of difficult to analyze by human and by machine. And I'm adding this by machine thing because there's something that's really interesting about exceptions. I promised I'll get to this. Actually, I don't have my watch. Somebody's going to tell me when there's 5 minutes left. Is that right? Yes, thank you. But I want to know better, so I'm going to just real quick, entertain yourselves. Introduce yourself to the next person. To your right. All right, here we go. All right, sorry for the interrupt. So we have till 10:30. All right, great. What? More than that? No, I hate to be over the next speaker because they're gonna want to kill me, right? Okay, who's the next speaker? So I want to see if I get killed in front of my house execution style, it's that guy, or the Go people, or the Rust people, or my ex-girlfriend. There's a list. Wow. Okay, so that's kind of a long. There is a break, so I can chew into the break a bit. So then I'm going to afford myself to talk about the machine part in the human and the machine. I hate people, so the humans don't count, but the machine does count. That was a kid. That was a joke. I kid, but I hate people, right? So anyway, so the machine part is people tend to think like there's this whole mantra of zero cost exception handling. You've heard of it? So essentially the mainline code is unaffected by the exceptions being thrown because they have a table, it's a complicated solution. But essentially they inferred the position in the code from the IP. So anyhow, so the whole zero cost exception handling is actually a bit of a myth because code is slowed down by quite a few percent if you use exceptions even though you never throw them. And the problem being that whenever an exception could be thrown, the compiler has much less freedom to optimize code by doing code motion, which is a kind of a key optimization technique. Meaning they move code the way they want to make it better, right? And this whole code motion thing depends on the function having only one known exit point. So if they can't guarantee that, then code motion is not done anymore. And this is actually so bad that C++ has a feature to allow people to tell the compiler this function actually does not throw, which is no except. Thank you very much. No except, it's kind of funny, it's not statically checked. And kind of proudly so from the body language as a fine gentleman here. But you know why? Because it can't, right? It's kind of a funny thing, right? It should, but it can't, so it doesn't, right? So it's kind of weird, right? So anyhow, so people needed this so badly that they added a keyword to the C++. I mean, it's a high cost kind of proposition add a keyword to the C++ language that introduces undefined behavior, ladies and gentlemen. I mean, you add a keyword that introduces more undefined behavior. They really wanted that. They really said, you know what, my life is not complete without this, right? My love life is not gonna make it without this no except thing, and that's exactly because the code generated not in the suspicion of exceptions. That's what, it's not only the presence, it's the suspicion, because the moment you have a function, a to y even, it can do anything, it can throw. So you call it from a different spot. Well, this function may throw, so what can I do? So then you mark the function as no except, and functions that call it can be optimized. It's a weird world, right? Where was I? The machine, too many paths. Okay, so I have these odd semantics. Composition with exception is weird. So do you know how many exceptions can you have in C++ kind of active at a time? Which version of C++? I don't know. 15. It doesn't exist, right? So choose the version and the number of exceptions that can be in flight. 1, right? Actually, it's not 1. It's unbounded. Because the exception that is happening during a catch, if you throw again from the catch, there's kind of 2. But in a different way, in an odd way. They're not both being thrown at the same time, but one is still active, which is, and then there's the whole unhandled exception and that stuff. So you can see all the discussion about that kind of stuff in the scope card article. So, there's kind of an odd thing here. So today's plan, we're actually starting the talk right now. I have 15 minutes to go. So we're going to use exceptions, but with the advantages of local handling, minimizing soft errors, making correct code easier to write. But I'm going to start with a few background items coming from completely different areas of computer science. Number 1, STD variant. Excuse me. STD variant, C++17 or Boost variant, what does it do? Yes, please. Loud. Get it. I'm going to repeat so you can. It's a tagged union, meaning it may have one of a few possible types, right? And there's information about which is valid, right? Great. They call it in kind of, if you want to be really scientific, they call it a sum type. Why do they call it a sum type and not kind of, I don't know, a difference type? Because the universe of values representable is the sum of the universes that could be represented by each type. If you have a variant of int and double, is all possible integers plus all doubles, right? So it's a sum type. Then we have STD optional, which is sort of a monument of bad design, but that's a topic for a different talk. We don't have time for that. It's like the worst thing that ever happened to the humankind. And we have boost optional, which is probably the second worst thing that has ever happened, which offer no extra information in the null state. So that's kind of a bummer, because we do want remember, I want to transport arbitrary amounts of information about an error when the error does happen. So this is kind of painfully close to what we want, right? We also have things like the maybe either monads, depending on the language you use in the functional world. So these are very close to what we want, except they don't have that nice piece of extra information about the error, the exception, the whatever bad happened. There's also kind of weakly related this whole notion of promise or future, T, which means it's either a value of type T or an exception, which gets very, very close to something interesting, right? But it's all about threads and stuff, so we don't want that. So here's my idea. So we have union types and discriminated unions and stuff, and that would be, for example, just as an illustration, I'm going to have a class either that is parameterized on 2 types, and I'm going to have a union of T and U, and I'm going to have a Boolean telling me whether the first or the second is valid, right? Nothing fancy here. There is something fancy though, change in C++ 11. Who knows what the change in unions was brought about in C++ 11? union in C++11 versus C++98? Dynamic types, no. Close, but not quite, that's not the essential thing. There's something really essential. Huh? Anonymous, no, anonymous is old. There's this very nice lady, Lois Goldwaite, who introduced this change, and I like to believe I influenced her a bit, because before C++11, a union could only contain types without constructors and destructors, meaning it was unusable. No, I'm not kidding. You could not use union for any practical, like any kind of code that had any pretense of being sophisticated and hip. It was unusable. So you'd have to do like atrocious tricks to make it work. So then, ever since C++11, Lois said, you know what, union should be just a mechanism to tell the compiler, please put these fields at the same address and leave everything else to the user. And that's the way it should be. Union should be a layout painting mechanism. That's it. Right? So this is great. These guys are allocated at the same exact address. They live literally one on top of each other. And the size of the union is the maximum. Thank you very much. And then we have the bool, which is kind of not very efficient, but you got to have it. Great. So that's the discriminated union thing. So here's the idea of expected. So let me introduce to you this whole new idea, which goes the following way. It's not a biggie. We want to express the union of an overt type and a covert type. Meaning, in the normal case, the value of the overt type is there, which would be the t. And in the wrong case, an e is going to be there. And it's going to have an extra information about what happens, and it's going to be eagerly constructed but not thrown yet. So e is going to be your exception, and t is going to be your normal return. So an expected TE is either a T or an excuse. E for excuse, right? So it's either the T, it's all the possible values of T, thank you, or a reason for which the T could not be produced. But nothing has been thrown yet. It's kind of magic, right? It's encapsulated. So then you return this guy from a function such as a to I, and then the user can look at it or can just use it. So I mentioned this, I told you a bit about this. So these are the nice gentlemen who took this idea to the standardization committee, and kind of they went through the hoops of standardizing it. Vicente and Jeff Bastien, they ran with it, and there are implementations available by actually these two folks and others. And I don't know if you want to Google for it, this is kind of the number. But if you just Google for C++ expected, you're going to find it. So it's actively discussed for C++20, and many details are still in flux if you look at the text of the proposal and stuff. And the funny thing is, you can influence the process. I literally, like, you people in this room and you people on streaming. By the way, is this kind of streamed, recorded? All right. So they told me to send us the recording, and we're gonna beat people with the recording, right? With the USB stick. So what you can do, if you like this or if you don't like this, you can write these fine gentlemen and say, you know, I don't like this particular aspect or whatever, right? So you can actually influence the process. A lot of details are still not really quite established yet. So I'm going to discuss a few of those. So the nice thing now is that in the very signature of the function, you can express what happens. So a to I would return an expected of int and some error type, which could be like as simple as an enumerated type, right? Or it could be something more sophisticated, like something derived from std exception. It's up to you. If you're on local, you can check the result. You know, put this guy into a result, and it's you call the has value method, and you can get the error. And if you simply want to use the result, you have this interesting syntax here, which goes if result use star result, which is kind of a pointer-like syntax. But this is not a pointer. And that will be a precedent. And this is one of the aspects being discussed, like in the standardization community. Do we want that or don't we want that? Who was the first to use this syntax for something that's not a pointer? remember what I told you the worst thing that happened to humankind was? STD optional. STD optional has that. It shouldn't have, but it does. All right, great. So if you want centralized, you just use star result without checking it. And if you use it, what do you think is going to happen? It's going to either return an int or it's going to actually throw the error if not. Right? So you can actually be nice. No, you can be really thorough. Look at the error. You can be just nice. I'm just gonna code for the happy I'm gonna test and code for a happy case, or just use the happy case without checking. And in that case, only in that case, you're gonna get a throw. Right? So great. So let's analyze a bit. We're gonna get into the implementation just a bit, but let's look at what we have right now. The top level. What was the idea? Well, expected associates errors with computational goals. That's really I'm proud of that sentence. It's a fancy sentence. It has all the right words, right? Associates errors with computational goals. I mean, you gotta be there, right? I love it. Can I get a hand? Come on, you guys. Thank you. Yes, this is awesome, right? I love it. You know, I'm gonna put this in my email, like at the bottom there, like. Naturally allows multiple exceptions in flight. So you can actually collect exceptions from multiple calls to multiple functions. You collect these exceptions, you put them together, and you handle them separately. So there's no more like, oh, you can only have one exception, whatever, right? You can switch between the error handling mode and the exception throw styles. So you can code in either the C style, the Go style, or the C++ Java style, right? It's up to you. You decide. You can teleport the exception, across thread boundaries, which is kind of a difficult problem in C++. Kind of, I want to catch an exception here, pass it to the other thread so you can handle it and that kind of stuff. So that's kind of a difficult thing. And with expected, you can do that easily. You can across no-throw subsystem boundaries, interfaces with C and stuff. You can teleport across time, save the exception now and throw it later. It's pretty much like any other C++ thing. It's not special anymore. You can collect, group, and combine exceptions. So that's great. So let's look at the implementation. It's just for exposition purposes. The actual implementations don't need to be exact like that, but this is kind of a possibility. So this is my whole state union with TA and ENA. All right. I like to have the same length. So the code aligns nicely on the page. Right? If it was like yes and no, you have yes 3 letters, no 2 letters, you're ruined. You're screwed, right? It's terrible. Okay, I couldn't find the 3-letter version, so okay is okay. True. And by default, here's the bias. And this is kind of an important point. What is the natural state of an expected? Does it have a T in it or an E? If kind of make no commitment. What do you think? A T, because somebody said E, right? So it's kind of already a controversy. And by the way, that was discussed in a committee. But my personal opinion, and it turns out the proposer's opinion, is that by default it should be an E. Default constructed T. Sorry. Yeah, I kind of ruined my whole thing, right? So by default, I'm expected to have a T in there, so it's going to be a default constructed T. If I do nothing with it, that's why that okay by default is true. So to wit, my default constructor here is going to create a T at the address of yay. Yes? You know the syntax, right? Yes. So create at the specific address. It doesn't call the operator new, right? It's just. So this is just syntax for saying, please construct a T at the specific address. And we need to do this kind of stuff because you remember that we have a union here which leaves everything to you. It's your responsibility to initialize and destroy things properly because the compiler doesn't know what's in there. Is it a yay or is it a nay? So you know, right? So I could create an expected implicitly from a T, which again is going to construct a T from the right-hand side. And notice that this is implicit, right? So if you have an expected of int and whatever, and you pass it a 5, it's gonna initialize the expected thing properly. Yes? Question? All right, so here's something unexpected, literally, right? There's a new type, unexpected. And I need to create this constructor that takes not an E, which would be expected. Oh my God, this is kind of a huge overload on words. But I need to wrap it in a separate type, unexpected, and I expect you to give me the answer on why was this necessary. Something who is not a speaker, because I know speakers know everything. Yeah, I know this. Messed up, yes. Why would I need not an E, but instead of a wrapper around D to signal to the compiler that things are different? This ambiguity. What would be the ambiguity? Yes. Aha. I could have an expected of int and int because I'm a jerk like that, right? It's just I want to. I mean, there should be nothing stopping me. But actually, it's even worse. I could have an expected of int and short, or int and long, or I kind of slightly different types. I could have an expected of base and derived, right? So because of that, when I construct an expected, I gotta know what I'm doing. So imagine T and E are identical for the simplest case. So in that case, this constructor takes an int and makes a yay, yes, makes a good object. But this guy would take an E and create a bad object, so it can't be the same thing. So therefore, they wrap it in an unexpected object. So that tells the compiler, oh, this is the bad case, and that's the good case. But bear with me, because we just transported a problem elsewhere. What if T is unexpected D? That's not allowed. Problem solved. So you can't really, you can't in the specific, you can't have T to be an unexpected of something, right? So by law, they just said, you know, you can't do more than 60. It's just, this is like, this is the limitation of what the feature can do, which I think is reasonable, but it's kind of interesting to kind of see we do have an infinite regression problem here, right? Because we need to disambiguate. So, okay, expected of a constant, unexpected, whatever. Yes? Question? All right. So I said all the right words so far. Great, thank you very much. So in that case, I need to initialize okay with false. All by default is gonna be true, so I don't need to do anything when it's true. HDMI 2 is great, not input is detected is awesome. And I think it's my screensaver. Thank you, Victor. All right. I'm on battery. I just remarked I'm on battery. So we gotta click on this really often. All right, thank you. Where were we? So in that case, I'm going to construct the address of NA, which is actually pretty much the same as the address of VA, but just for clarity, I'm going to construct an E of RHS.value. Guess what value gives you if you have an unexpected? It's going to give you the E that's inside. Unexpected is really a trivial, boring type. It's just a wrapper on an actual object. It doesn't do anything interesting except it tells the compiler what's going on. Now we have kind of a more odd thing. We have this explicit expected of you, which is one of these things. Who knows about this kind of stuff? Just gauging. Who knows about R value references? More hands. I mean, I said this and then R value references. I got more hands. Thank you. So, okay, I have 5 minutes, but this is really funny. So here's the thing. This looks like an R value reference. It's not an R value reference. And in case you didn't know R value reference, you're better off because I'm going to tell you right now, this is awesome. So this is introduced in C++11 R value reference. And whenever you have a double ampersand after a type, it's an R value reference, except when it's not, as in this case. In this case, it's called a universal reference, except it's not. So the funny story is Scott Myers kind of figured this out and said, you know, there's got to be a name for it, which this is not an R value reference because U is a template argument, is a generic type, it's not a specific type. Whenever you have generic type followed by double ampersand, it's not an R value reference. It looks like one, it's something completely different. So Scott Myers was, well, we got to find a name for that. Let's call it universal reference. So he wrote effective C++ and what, he wrote about it. And the top people in the C++ standardization committee, I'm seeing laughter here, I know he knows. So there's kind of a directive at top level in the C++ committee. They said, we got to find a name for this, anything but universal reference. Somebody doesn't like Scott Myers on, at the top level. I'm talking top people, okay? And there was a paper, this is not a joke, this is the truth. There exists a paper, official, like ANSI, ISO, whatever, right? I don't know, the president signed it or something, right? That kind of stuff. It's a presidential whatever, right? There is a paper that explains why the choice of name was not universal reference. I'm not kidding. This is a paper. It's not kind of a note. It's not like an email. It's a paper written by top people, okay? You gotta look for it. All right, so this is a universal reference, and it means whatever it passed, it's gonna match that. R value, L value, const, non-const, whatever nonsense, etc. It's just gonna match, meaning I'm going to be able to construct unexpected from anything that forwards into this T type. So if you have an int and you initialize with a short, it's gonna work and that kind of stuff. All right, so this is the initialization, the copy constructor, which is nice. If okay, I'm going to construct a T, otherwise I'm going to construct an A, so pretty obvious. This is kind of, again, the R value reference. No, not again, sorry. This is completely distinct. This is an R value reference here I'm going to construct by moving, and that kind of stuff. And here comes the operator star, which is, remember the dereference thing? If the object is not good, I'm going to throw nay, otherwise I'm going to return a. Right? Okay, now you should know there's a kind of a discussion here because some people say, oh, you can't throw nay. You gotta throw a wrapper on top of nay, which is called bad access exception. Or some, it's one of those names, right? Because people say you shouldn't throw kind of anything, you should throw something that's derived from STD exception. And that's a discussion that, again, you can help settle. You can actually help. I want to throw that or I want to throw the other. And here we have kind of the whole menagerie of like const overloads and R value const and all that nonsense. And then we have the arrow operator, which does pretty much the same thing. And we get the error. The same with kind of overloads and stuff. It just gets the error object without throwing it. So you can actually access the error object. Thank you. Great. Has value return. Okay. Explicit operator bool. What does that help with? Explicit operator bool is the fancy way of saying I can test this with an if. If whatever, then whatever, right? So that's a nice thing. And you can get the value, you can get the error as on the previous slide. You have like value or, give me the value or this guy, which is kind of useful. And this is kind of the last thing I'm gonna discuss today, which I found interesting, is the swap function. Swap. Who knows enable if? All right, who knows the many subtle distinctions between enable if and enable if T? Fewer hands. Okay, only the speakers and one guy. Okay, thank you very much. So anyhow, I'm not gonna insist on this, but swap has a difficult job to do. By the way, this is kind of lowercase e. Sorry about that. Swap has a difficult, so you want to swap, right? And usually it's easy because you swap like the same types. But in this case, swap sometimes need to swap something of a type with something of a different type. Right? So there's got to be some complication there, right? So let me start with the simple cases. If okay, and the right-hand side is okay, fine. I just swap yay with RHS.yay. All good? We're good? All right. Otherwise, I'm going to just defer the problem. I'm going to swap the other way. Else. So I'm on the not okay. If not RHS okay, both are bad, so I'm going to swap the nays. So far, so good? And the complication goes in the dot, dot, dot. Right? Yes? So these are the easy cases. The first easy case is both are of the type T. This is the other nice case, both are of the type E. This is kind of going here because I just swapped the arguments, right? And this is kind of the hard case. Like I have to swap two things of different types. How would you do that? You're software engineers, right? How do you do that? Swap two objects of different types. Huh? With a temporary, but what do you put in a temporary? I mean, it's kind of a difficult thing, right? So here's what you do. Well, number one, you're going to create a temporary, thank you very much, by means of moving from nay, because I know nay is good. Then I'm going to destroy the nay, right? Then I'm going to create at yay, I'm going to construct, at the address of, so nay and yay have the same address. So by this point, the object is clean, right? Now I'm going to construct at the address of yay, I'm going to move from RHS.yay. I'm going to make OK true, and then I'm going to go on the other side to RHS, and I'm going to ruin his life, right? Then I'm going to create the exception, and I'm going to set it to false. However, there are only some circumstances under this can work, ever. And I'm talking exceptions. What if this guy throws? What happens? What? The world ends, pretty much, yeah. So you can't, this is a kind of a very interesting case in which you can't even write the swap function unless it has a no-throw move constructor. That's why this whole enable if business. I say this function is defined only if, and here are some introspection items, is no-throw move constructible v of t, and is swappable v, and is no-throw move constructible e, and is swappable e. Only under these circumstances I can even think of defining swap, otherwise I'm not allowed to even define it. Because you just can't define it. You don't have enough pieces on the board to define it. It's a very interesting situation. And actually I found a bug in the implementation, that kind of stuff. So this is kind of, again, an ongoing discussion. So it's interesting. So typically the way you use this, and with this we're kind of done. So I say expected of double runtime error good, gets 100, the implicit conversion all good. It's 100. Start good is 100. And then I'm going to say something like I want to create a bad one. I'm going to say expected double runtime error bad equals unexpected runtime error. So unexpected is also kind of a convenience function. I initialize the unexpected type and all is good. So I'm going to assert that it doesn't have a value. It has an error in it, an exception. If I define a function, I can return unexpected and return runtime error. On the happy case, I just return a computation. It's going to initialize the expected return appropriately with a double. All right, so if you just use centralized, you just put a star and you're done. You say double growth equals star relative or whatever, and it's just going to work. On the happy case, it's going to throw an exception on the unhappy case. And it's pretty much this is just like exceptions. So you have the option. Really nice. With local error handling, of course, you can test it with if. Remember explicit operator bool. And that's pretty much easy. And I have one question for you. What if I have an expected that is bad? Sorry, expected was like this kind of misspell. What if an expected object is bad, but nobody actually attempts to use it? Should it throw during the extraction or not? Because there was an error after all, but the error was not visible. Do you think it should throw from the destructor or something? You should signal the error? No, the error was intentionally ignored, right? It's like the tree in the forest. Thanks, this is great. So checkpoint, we associate errors with computational goals. Again, my favorite sentence in the whole talk. We allow multiple errors in flight. We can teleport across thread boundaries, no throw subsystem boundaries. You can teleport across time. You can collect, group, and combine errors. You can have much better code for the compiler to work with. And we're kind of late here. So destroy. Thank you very much. Thank you.
Thank you, Andrei.